Hi, and welcome back to our videos before class. I know it's been a while since we've done these, but just wanted to give you a little bit of preliminary information before we try to see how this online lecturing is going to go tomorrow. I assume you'll be watching this on Sunday, or maybe even Monday morning before class. Either or. Be nice to get back into actually teaching some material and see how you all are. Anyway, so before break, we talked about hypothesis testing with variances, and we didn't have a chance to do a problem that had testing a ratio of variances. In particular, remember back when we were doing hypothesis testing with means, a lot of our assumptions was whether or not the variances of the population were actually equal. So this is what doing hypothesis testing on ratios of variances is about, is seeing whether or not the population variances for two independent populations really are equal to each other or are potentially equal to each other. So this is problem 7.4-9 in your text. The important part here is that we've got random samples from two populations, X and Y. We've got the mean and the variance information given to us, as well as the sample sizes. And we're testing whether or not the ratio of the variance of X to the variance of Y is 1 versus the ratio is actually greater than 1. So notice in this case it's a one-tailed test. But for the ratio of variances, we need to use a different distribution than what we've used in the past. So we've seen normal distribution for means when we've had large sample sizes. We've seen the t-distribution for means when we've had the small sample sizes. And right before break, we did the chi-squared distribution for hypothesis testing with just a single variance, a single population variance. So here we need to come up with a different distribution to use. So when we have the ratio of variances, remember, these aren't quite distributed as chi-squared random variables, but if we do the ratio of the n-1 x squared over sigma x squared, we know that's chi-squared of n-1, and the same thing on the bottom here with the y's. So, and then to get our f distribution, remember we have to do a chi-squared divided out by its degrees of freedom. So again, this n-1 sx squared over sigma x squared, that is chi-squared of n-1, so we need to divide it by n-1. Likewise in the denominator. And then when you simplify all of this, under the assumption that the null hypothesis is true, under the assumption that the variances are actually equal, this simplifies down to sx squared over sy squared. Since we're doing this particular ratio, we know this has an f distribution. The degrees of freedom on top is n-1. The degrees of freedom on bottom is m-1. So those are our numerator and denominator degrees of freedom, respectively. All right. So looking at our critical region then, we know that we have an f distribution, kind of looks like this in general. We're looking for the ratio being greater than 1, so we have a right-tailed test. So we need to figure out what this critical value is. We have 8 degrees of freedom for the numerator. We have 10 degrees of freedom for the denominator. So we need f sub 0.05, because they tell us that alpha is 0.05 in this problem, of 810. That's our notation. We find out that that's about 3.072. The way you could look up at your table in the back of your text or use Excel. The Excel command is what I've written down here. So it's f.inv. So this is the inverse idea, right? You give it a probability. It gives you the value associated with that probability. I use the .rt because it's a right-tailed test. We want a probability of 0.05 in our right tail. Numerator degrees of freedom again is 8. Denominator degrees of freedom is 10. So if you use this Excel command, you will get this value out. Okay. All right, so what's our test statistic then? Well, we already know that this is up here at the top, this is the random variable that has an f distribution. So I can calculate my test statistic by using the information that we have from the problem. They tell us that the sample standard deviation is 12.9 for X. The sample standard deviation for Y is 7.1, pardon me. So I got to square both of those to actually get the variances. So we do that and we get 3.301. that value is going to lie in our critical region because it's greater than the 3.072. So what that tells us is that we're going to reject H naught, and we have sufficient evidence that their variance for X is actually greater than the variance for Y. All right, so going back up to the problem now, if I scroll back up here, it says after you've done the hypothesis test for the ratio of variances, go back and then do the hypothesis test for whether or not the means are equal, or if the mean for X is actually less than the mean for Y. Since the variances now are suspected to be not equal, we don't use the formula that we had for the pooled variance when we do the hypothesis test for the means. We have to use Welch's T, with the degrees of freedom that's given by Welch, to be able to do this. So again, since the variances are assumed not to be equal in this case, because we had a hypothesis test that said they're probably not equal, the variance for X is probably greater than the variance for Y, we can't use the pooled variance to help us get the test statistic that we would need for the hypothesis test for the difference of means. All right, so the reason why we're using Welch's T again is because we have small samples. If this was a large sample, we would go with the normal distribution approximation and go and have fun. Okay, so this is small samples and the variances are unequal. That's what's telling us why we have to go use Welch's T to be able to do this hypothesis test. All right. Remember from Welch's T had that nasty formula. Again, everything from here on out is going to be all take home, so you're going to have your book, so there's not going to be any formulas that you're going to have to memorize to do any of these problems. So this is in your book. It's in section, I think, 6.3, or pretty sure it's 6.3. Whatever the section is for the confidence intervals for differences of means, that's where this formula is. Anyway, this is a formula that you would need to use to figure out the degrees of freedom, and then you take the floor. All right, so this is just the formula to plug in all the values that we have up here. If you do that, you get about 11.87 if I typed it all into my calculator correctly. So since we take the floor here to get the degrees of freedom, the degrees of freedom has to be an integer. Since we take the floor, we get 11. Remember, we just, floor means drop off the decimal part. You don't worry about trying to round. All right, so notice that this degrees of freedom is significantly less than what we would have done if we had done the pooled. Remember, for pooled, we would have added these two and subtracted 2, right? We would have done 9 plus 11, subtract 2. We would have 18 degrees of freedom, but since we've got this variance is unequal idea, we lose a lot of the degrees of freedom. What that means is that our t value here that we're going to get for our critical region is going to be significantly, maybe not significantly, but it will be a larger value than it would have been if we had more degrees of freedom. Okay. All right, so here's our critical region. Alpha is 0.05. We're going to the left here because we're testing that the mean for X is minus the mean for Y is less than 0. The notation, of course, for this value is t of 0.9. T said 0.95 of 11. Remember that the subscript is how much probability is above that point. I know it seems backwards, but that's the idea. However, we also know that this is since the t distribution is symmetric, independent of my bad drawing, the t distribution is symmetric here. So t sub 0.95 of 11 is the same thing as the negative of t sub 0.05 of 11. So you can go into Excel. I didn't write the command down here, but if you go into Excel and use the t dot inverse dot right tail, you can get this 1.796 value, and we want it negative. Or you could just do the t dot inverse and use 0.05, because remember the t dot inverse command is cumulative from the left. So, and you would still get the negative 1.796. So this is our critical value. All right, so our test statistic now is what we would use is the same test statistic if we had large samples, right? We don't use the pooled variance test statistic. We use it like we would have large samples. So we would do the difference of our means, our sample means, so the 93 minus the 132, subtract off what we think the difference is from the null hypothesis. In this case, we're assuming they're equal, so that difference would be 0. And then we just divide by the square root of what the variance estimates would be. So remember that for the sample mean variance, we would do the variance of the population divided by the sample size. So that's why we got 12.9 squared over 9 here. And then the same idea for the y. And then we add them because we're assuming they're independent populations. So this is the same denominator, the same standard deviation estimate we would use if we had large samples. When you go through that, your test statistic is -8 and change. That's definitely well within our rejection region. So we're going to reject H0 here and say that our mean for X, it really is less than the mean for Y. Or technically, we have sufficient evidence to conclude that the mean for X is less than the mean for Y. All right, we're going to do another example in the second video of a problem where we're going to do a two-tailed test rather than a one-tailed test. And we're going to do that on Excel to show you how we get the different values for the F statistic.